First, I'd like to thank Ravi and Amita for the invitation. I am a certainly odd person here. I think I have not worked on laser and matter. So I was told by Ravi that I should talk about general computational platform, which you could think of under collaborative efforts. So I will basically talk about MHD turbulence. And again, these are published papers some 15 years back. So I'll go from the beginning and I'll try to show how simulations have helped us to kind of resolve some of the issues. And hopefully some of it may be useful for this work. There's one part which I've been discussing with Ravi especially. Our protostar has a magnetic field generation, and that may have some connection with laser induced magnetic field. There are some papers recently which have appeared. So maybe that we can discuss a bit later if time permitting or privately. So the one reference which I like to refer is 2004 physics report. So let's start with this equation MHD, which is possibly under some regime of collision limit, it will be applicable to probably your system. So U is the velocity field. I mean, this everybody knows. So I just want to say a few things that I'm going to work with high Reynolds number and high magnetic Reynolds number. So here waves are basically they are scattering so intensely among each other. So we really don't see waves. They are all basically extremely non-linear regime. So first theory came in 1965 and 64, Kraichan-Iroshnikov. So the question is MHD turbulence like fluid turbulence, Kolmogorov, 5/3, or is it different? And Kraichan and these two people thought that it is not Kolmogorov. The reason why it is not Kolmogorov is the mean magnetic field or the magnetic field of the large eddies will determine the length time scale. So the time scale for fluid turbulence is, if you recall from Kolmogorov theory, is time scale is 1 by L by VL. So VL is a velocity at that particular scale, but here they thought that it is not this VL, but it's B naught, mean magnetic field. And this mean magnetic field, if there is really no mean magnetic field, but there are fluctuations, a large scale eddy, that particular eddy has a B naught and we can use that. And then it changes the spectrum. And the spectrum we can, this simple dimensional analysis, it gives you K minus 3/2, not 5/3. So I hope everybody knows about Kolmogorov's very famous theory. Let me just say, in case people are not aware of it, a fluid turbulence theory, EK, spectrum in the inertia range is K minus 5/3. And this flux is the energy flux which goes from the large scale down to small scale. Now this stayed on for long time. This minus 3/2, most people believed that to be the case. Now this was generalized in 1980, again similar formalism, but it was, this paper by Kraichan is only 1.5 page long. It's really 1.5 page long. The wave scattering, the time scale is that, and it's kind of surprising that you believe that 1.5 page paper, very intuitive paper. But this was generalized bit later in 1980, and then this PRL, these are physical regulators, where the waves Z plus and Z minus. So I'll write that equation as well, Z plus and Z minus. So these are alphane. Z plus, if you recall, is U plus minus B. And these variables, they interact. In fact, I need this. So let me write this plus minus. So there are two. Instead of writing for U and B, we write in this Z plus Z minus. Z minus plus dot grad. So we ignore the viscous terms. Okay. So this is my equation. Now interaction is basically because of this knowledge interaction, and this is a alphane propagation. So this is a vector field. Okay. So now according to Dobrowolny et al., they say the random scattering are alphane waves that will scatter this Z plus and Z minus, which again Kraichan had the ideas, and but is probably put in more concrete footing, the random scattering and so on, and one can derive the expression for fluxes of pi plus and pi minus. This flux is a flux transfer in the Fourier space, large scale energy going down to small scale, and they are equal. According to this theory, they are equal, pi plus and pi minus, irrespective of what is E plus and E minus. Okay. So if I have E plus bigger, that means Z plus has higher energy compared to Z minus, which is the case in the sun, near the sun surface. Their alpha n waves, outward alpha n waves are more energetic than inward alpha n waves, but this is equal. Now, there was theory which came, so well, let's try to see whether we can construct Kolmogorov-Like theory for MHD turbulence. And how can that come? You can look at this term, the nonlinear term, ignore this. If you ignore this term while saying, well, this B naught is not too large or not impacting so much, and then one can say the time scale will come from nonlinear term. There are two time scales because Z plus and Z minus have different time scales, and that is the time scale, and that gives you this. Okay, so spectrum is for this is, well, I didn't write the spectrum, I think. Spectrum is minus 5/3. I can invert it, pi plus and pi minus. So inversion of this equation for E plus and E minus gives you minus 5/3, and E plus and E minus need not be equal. So that is what is a theory of, this was first written by Kurt Marsh in 1990. I worked quite a bit on this problem, and there is a more famous theory is Goldrich and Sridhar. They use critical balance, which I will not discuss in this talk, and they also claim that spectrum is minus 5/3. So these are competing theory. Kraichan, Dobrowolny is minus 3/2, and there is 5/3 theory. Now which among the two is correct? Of course, we can go to simulation or experiments. Experiments is very good experiment is going on outside, which is solar wind. So the plasma coming from the sun, and that, okay, so solar wind does prefers minus 5/3. So there was, way back in 1982, there was a paper by Goldrich and, sorry, not Goldrich, Matthews and Goldstein, and they had shown minus 5/3 like spectrum, close to minus 5/3. So the question is, which of the two is true? So we started looking at it from simulations. So this is where simulation comes into kind of useful method or useful tool to verify which among the two is true. One thing to notice is that 3/2 and 5/3, 1.5 and 1.67, they're too close to resolve in a simulation, the spectrum. There will always be error, and it's very hard to resolve that. So what we try to look for is this flux prediction, pi plus and pi minus. If you recall, Dobrowolny wrote that this is equal, pi plus and pi minus is equal, but according to Kolmogorov-Like theory, they are unequal. In fact, we can rewrite that E plus by E minus is this ratio. Now this can be tested. I can take E plus and E minus to be very different, let's say factor 10, and that should show you whether these are equal or unequal. And this is what we did in 1994, that was a PhD work, one of the chapter, and this is, I mean, there are a lot of things in this paper, in this figure, but you can look at the fluxes. E plus and E minus are unequal, here E plus and E minus, and Z plus and Z minus, these are fluxes. Pi plus and pi minus is sitting way down here. So pi plus is bigger. So the alpha in waves coming from the sun, Z plus has higher flux, energy flux than Z minus. That means Kolmogorov is correct. So this, we knew that Kolmogorov is really better model than Kraichan for MHD turbulence. Now the question is, what is going wrong with the Kraichan's argument? Kraichan said that it is B naught or mean magnetic field or the large eddy B naught determines the time scale. It's true, I mean, alpha waves go like this, and the B naught should determine time scale, but then it's not quite the whole story. In fact, this is a physical intuition which works according to me. Of course, we need some more simulation to get into this in more detail. So this is a physical picture, okay. So we have an alpha wave sitting here. So let me make a kind of crude model. So when we go mountaineering, you know, trekking, so we don't see the mean slope of the mountain. We see local terrain slopes. So the question is, the alpha wave of this wavelength, is it going to see only the mean magnetic field, or is it also going to see other fields? So this Alfvén wave, small one, small wavelength Alfvén wave, is going to see the Alfvén wave of slightly bigger wavelength. So it is riding, well, basically is riding on the bigger Alfvén wave, and that bigger Alfvén wave is riding on another bigger Alfvén wave, very similar to what happens for Kolmogorov theory of fluid turbulence. So the mean magnetic field, effective mean magnetic field for this guy is basically determined by the Alfvén wave of higher wavelength. In fact, that does come out from mathematical theory, which I will not describe here. I did this denomination group analysis, go scale by scale and see what B naught is coming at different scales. It's exactly like field theory of high energy physics, what is done. You, like electron charge is getting renormalized. Similarly, the mean magnetic field effective for this for any wavelength, Alfvén wave, gets renormalized, and this B naught is K dependent, K minus 1/3. Now, if I plug that in the Kraichan formula, then I recover 5/3. So if I put it here, EB, so this is Kraichan formula, minus 3/2 in 1965. I just had to replace this B naught by this, and then I very nicely get minus 5/3. Okay, so this is how it kind of makes consistent picture with simulations and experiments. Experiment means a solar wind that we get 5/3. Now, question is it really true for large mean magnetic field? Now we can apply large magnetic field. For example, in the sun there is a mean field acting on the corona or on the photosphere, or probably, I mean, in some experiments in lab you could have very strong magnetic field. Now this is one recent work. So we are asking the question when B naught is much bigger than delta B. Now of course there are already some work which has been done. This is called weak turbulence theory. So B naught much bigger than delta B, weak turbulence theory should work, and one prediction is that 1 by k squared is a spectrum and is anisotropic. So this needs to be investigated in simulation. So this is isotropic flow when B naught, so this is for fluid actually, this is not for MHD, this is very isotropic, this vorticity squared, omega squared. Now when B naught is 10, this is for B naught 10. So this is omega squared and these are Taylor columns, not these are columns, basically columns. Velocity field is basically going like that. It's a quasi 2D. This is recent simulation by one of the student of, I think US student, Sita Sundar, she had done this work. So we can analyze this for B naught 10. So this was B naught equal to 10. Now we can look at spectrum. Now spectrum is of course anisotropic. How do I analyze a spectrum which is theta dependent? And theta dependent spectrum is analyzed by making rings. So this is another thing we can do. We can make rings in simulation, of course is easy to do, and you can look at energy contained in the ring. So it gives you anisotropic picture, this function of theta and this function of theta. So energy is more concentrated near the equator, near theta equal to 90 degrees, and so that's what is signaling that the flow is quasi 2D. So naturally if a mean magnetic field is that way, the velocity field basically goes around like that, and so it's quasi 2D. There is UZ, there is UZ up here, but UZ is not significant, U per P is very significant, and the whole picture is very different. I will not get into the details. 2D hydro ideas start coming into play. So the inverse cascade here of 2D hydrodynamics, so inverse cascade, and this is very different. So I really doubt whether weak turbulence theories can capture all this phenomena when B naught is 10. Okay, so that's we are trying to look at this in some more detail. Well, in a lot of detail. In fact, this requires major rework in terms of simulation. So this is what simulation can reveal: the phenomenology, which is true, which is not true. We are sure about 5/3 for B naught order 1. Mean magnetic field is order 1, but for very strong B naught, I think we need to look at it more carefully. I'll just show one more slide. What happens with Rayleigh-Bernard convection? It is mandated that I should talk about power of simulations. So we did a very heavy simulation with on 4000 cube. This is really heavy. I mean this is full. Well, basically in this supercomputer in Kaust in Saudi Arabia, We ran 64,000 processors, and the spectrum. So this was unresolved problem, and the spectrum we find that it is basically 5/3. And you can see that decades. So the what in this community we say how many decades of 5/3. So I go from here till more than a decade of 5/3 we get here. It is normalized, no? So I multiply this by 5/3, so it should be flat. And indeed we get this. And this was a big problem. I mean, Rayleigh-Benard convection. What is the spectrum? You could also figure out from simulation. So simulations come very handy. Of course, this really take a lot of computer time, and of course require very big computers to run them. So they can help us resolve. So I think that's what I will stop. I just make one. So I'm interested in talking about this bit maybe privately. So we can. So what happens with protostar? So this MHD that may have some similarity with laser-induced MHD if it is there. Okay, so I'll stop. Thank you.
I mean, you mentioned initially that the cascade always goes one way, long wavelengths down to short wavelengths. But at the end there, you said you've got the inverse process going on.
Yeah.
So is that because you've got a reduced model? What's happened there?
Okay. So in 2D hydrodynamics, there are two conserved quantities. In inviscid limit, when viscosity is 0, then energy is constant, u squared, and entropy, omega squared integral dx is constant. And then it was shown by Kraichan that as a result, energy is, suppose I have 4 sets of wave number k and f, energy will flow backward and entropy will flow forward. So 2D hurricanes are formed because of inverse cascade. Energy goes from small scale to large scale, but that happens only in 2D hydrodynamics. So this is called inverse cascade, and with strong mean magnetic field, flow tends to be 2D, and that's where this effect comes. Like rotating turbulence, that kind of things happen. So, so when I said forward cascade for MHD, I mean for when B naught is order 1. That's
okay, there's any? If not, let's thank the speaker again.